All right, we're back. We are on page 3 of Calc AB Notes 8. We're talking about L'Hopital's rule, which is one of the coolest things that you learn because it really simplifies a lot of the work that you have to do. So you have to first realize that you're dealing with a limit where the limit of the numerator and the limit of the denominator are both 0, or they're both infinite in some way, either positive or negative infinity. So things to watch out for. Don't overuse the rule, right? If you get 0 over 5, that's 0. Just because a 0 shows up doesn't mean use L'Hopital's. If you get 5 divided by 0, that just doesn't exist, right? It's not 0 over 0, it's 5 divided by 0. Can't divide by 0. That's not an indeterminate form. That does not exist. Also, you're not using the quotient rule. I never see anybody really do this because the quotient rule is more work than L'Hopital's rule, but it's not the quotient rule. It's the derivative of the numerator and the derivative of the denominator, like not a quotient rule situation. So let's see if we can do it. So we're going to try to do really good work on these so that you just get in the habit of doing it. So here we go. I'm going to say, now, should I say that f of x and g of x, should I define f of x and g of x? Maybe. It depends on how much I want to write. I'm not going to do that. I'm going to actually just say the limit as x approaches 3 of x cubed minus 27 is equal to the limit as x approaches 3 of x minus 3 equals 0. Okay. Therefore, by L'Hopital's rule, this is like perfect work, which I don't really want to do all the time, but like you kind of have to. By L'Hopital's rule, the limit as x approaches 3 of x cubed minus 27 over x minus 3 is equal to the limit as x approaches 3. Okay, so now I'm going to use L'Hopital's rule. So all of that was set up. You should do that. You want to get as many points as possible on free response questions, so that's why we're doing it. So L'Hopital's rule says, if you get 0 on the top and 0 on the bottom when you do your direct substitution or you take your limits, then you're allowed to take the derivative of the top, the derivative of the bottom, and consider that limit. So the derivative of the top is 3x squared. The derivative of the bottom is 1. When I evaluate this, I get 27, so that's the value of the limit. That's all it tells you. Well, it's not all it tells you. I mean, that's amazing that it tells you that. So let's try this one. So the limit as x approaches 0 of sine of x is equal to the limit as x approaches 0 of x, which equals 0. Okay, so we get 0 over 0, basically. Therefore, by L'Hopital's rule, what is that? By L'Hopital's rule, it's like, I'll abbreviate, but come on. The limit as x approaches 0 of sine of x over x equals the limit as x approaches 0 of, all right, let's apply the rule. So we take the derivative of the top, we get cosine. Derivative of the bottom, we get 1. And then the cosine of 0 is 1. So these are actually the problems that we did before. Now we're just using L'Hopital's rule on them. So I'll be honest with you, when I'm just like flying through problems using L'Hopital's rule, I don't write out the like limit part. I should get in the habit of always doing it. It's old habits, man, they die hard. So that's why you're never going to get into the habit of doing it the wrong way. I recommend that. I recommend in life you do not develop bad habits because they are harder to break than they are to never get. So let's see. Limit as x approaches 1 of x squared minus 1 equals the limit as x approaches 1 of x squared minus x, and both of those limits are 0. Okay, so we can use L'Hopital's rule. Therefore, by L'Hopital's rule, the limit to the original limit, this is the part I really hate doing. It's just so much extra writing. But you know what? It's what you got to do. So there are options on this one. You could factor and cancel. Like there's often other ways to do it. If L'Hopital's rule applies and you are good at taking derivatives, which you should be, this is the way to go because it's just faster. Equals the limit as x approaches 1 of, use L'Hopital's rule. Got to take the derivative of the top, derivative of the bottom, see what that does. 2x over 2x minus 1. Okay, so if we let x approach 1, if we just substitute 1, we get 2 divided by 1, so we get 2. And that's it. Now, this one you probably would have factored and canceled. Nothing wrong with that. In fact, it's the right thing to do. So let's look at this. So this is slightly different, right? Like very, very slightly different, but still slightly different. The limit as x approaches infinity of the natural log of the square root of x is not 0. It's actually infinity. So if the denominator also goes to infinity, we can use L'Hopital's. So the limit as x approaches infinity of x squared, I don't know why I'm putting that in parentheses, but I am, is also infinity. All right, so it's basically infinity over infinity, which means we can use L'Hopital's. Therefore, by L'Hopital's, the limit, so the original, it's slightly advantageous to say like let f of x equal the natural log thing, comma, g of x equal the x squared. So then you can just say of f of x, of g of x, and like it's less writing. So like maybe I should also develop that habit. Whatever. I mean, you know, good habits are good to have, but I don't have all of them. All right, let's do it. So we're going to infinity. All right, I will share with you, and I've probably shared this before, that the natural log of the square root of x is the same as the natural log of x to the 1/2, and then that's the same as 1/2 the natural log of x. And I think it's easier to find the derivative of 1/2 natural log of x because it's actually just 1 over 2x, and you're done. So like I recommend doing it that way, but it's up to you. 1 over, so then I should, you know, do it correctly. So the derivative of 1/2 natural log of x is 1 over 2x all over 2x. Derivative of the top over derivative of the bottom. Now we take the limit. First, what I'm going to do though is simplify this a little bit. Limit as x approaches infinity of 1 over, let's make it 4x squared. This definitely goes to 0. Okay. And that's all it takes. I mean, you got to be organized. You got to think about it. Let's see what we got here. Why are we approaching from the right, do you think? I don't really know. Like cosine of pi over 2 is just 0. Sine of pi over 2 is 1. So like, I don't know. Every time I see that from the right, it makes me think somehow a log is going to get itself involved. But I don't think so. Let's do this. Let f of x equal cosine of x. I'm trying to up our game. G of x 1 minus sine of x. Okay, the limit as x approaches pi over 2 from the right of f of x equals the limit as x approaches pi over 2 from the right of g of x, and both of those are 0. Okay, so I think I've saved myself a little writing. I don't really know. Therefore, by L'Hopital's rule, the limit as x approaches pi over 2 from the right, for some cryptic reason, I'm not sure why, of f of x over g of x is equal to the limit as x approaches pi over 2 from the right of what's f prime. So we're doing f prime over g prime. F prime is negative sine of x. G prime is the derivative of 1 minus sine is, oh, maybe I know now why we're doing this. We'll see. Negative sine, the derivative of negative sine is negative cosine. So this will be negative cosine of x. So we're actually just finding the limit as x approaches pi over 2 from the right of tangent of x. And this, to me, explains why that pi over 2 is there, from the right, rather, because tangent, if you recall, look at all this space. If we graph tangent, it actually has an asymptote at pi over 2 and negative pi over 2, and every pi after that. So here, right? So 3 pi over 2, 5 pi over 2, like pi over 2 plus pi n, you're going to get an asymptote. So we need to know if we're approaching from the left or the right to know if we're going to get infinity or negative infinity. So that makes some sense. Now it makes sense, right? You knew there was a reason. I didn't know there was a reason. You suspect that there's a reason. So if we approach from the right, that's like this. That's a really thick, no, that's the one I use. All right, so this is just going to be negative infinity. So you don't need to get a finite value. You could get that the limit doesn't exist. You could get negative infinity, positive infinity, like whatever you get. Just make sure you're still allowed to use L'Hopital's rule, right? So simplify when you can, then try to take the limit. If you still get infinity over infinity or 0 over 0, use L'Hopital's again. But in this case, we just got negative infinity, and that is the answer that we're going to get. So let's see what this next one is. All right, so I'm gonna do my let thing, let f of x, because I kind of liked that. Seems fancy. G of x, and you should get in the habit of like naming functions, because in the long run it'll make it easier on you when you're writing your justifications and things like that. You won't like accidentally copy a function incorrectly. Good habit to get into. So let f of x equal this, g of x equal this. The limit as x approaches 0 of f of x is the same as the limit as x approaches 0 of g of x, and both of those are 0. So the sine of 0 is definitely 0. The tangent of 0 is also 0. If you didn't remember that, we literally just graphed tangent, so you did know that. So we have both of these. So therefore, by L'Hopital's rule, so it's not that bad, right? I mean, so it's really annoying to write it all down, but not terrible. Therefore, by L'Hopital's rule, the limit as x approaches 0 of f of x over g of x is equal to the limit as x approaches 0 of f prime, which is the derivative of sine of 4x. So that's going to be 4 cosine of 4x, right, by the chain rule, over the derivative of tangent of 5x, which is going to be 5 secant squared of 5x. So it's secant squared of 5x times the derivative of 5x, which is 5. So 5 secant squared of 5x. Okay, so now direct substitution, the cosine of 0 is 1, which means the secant of 0 is also 1. So this is just going to be 4/5. And we got it. And that's it for this page. So I feel like I should go to the calculator and check some of these. So I'm going to do that, but I mean, if you are done with this video, then you are done with the video. I'm going to switch over to the calculator for like 1 second, punch them in, see that they're right or wrong, and then fix them if they're wrong, so you're going to miss out on that. But let's see. So I want to do the limit of x squared minus 1 over x squared minus x, comma x, comma 1. 2, that's what we got. I want to do the limit, natural log, square root of x. So it's really, for this one, it's a question of like, is our work good enough? Because we definitely know logs grow slower than polynomials. This was guaranteed to be 0 from like before we even started. Infinity, we get 0. The limit of cosine of x over 1 minus sine of x, comma x, comma pi over 2, and then from the right you put a 1 here, and we get negative infinity, which is what we got. That was the one I was the most worried about. And then limit sine of, so this is, you should check your answers. I mean, like, see how I'm doing this? If you have the software on your computer, get as fast as I am. Like, there's no reason not to. 4/5, there we go. If you have the handheld, I understand it is more annoying because it's just a little more annoying to type on the handheld. But you know what? That's what you got. So use it. Or you can type them into Wolfram Alpha. It'll evaluate these limits for sure. And it's like, it pretty much is like natural language, just limit and then do parentheses, like basically the way I was typing them in there. Wolfram Alpha will probably interpret them correctly. So we got all this. And what I'm going to do is end this video here, come back in the next video, do a little bit more. So I will see you there. All right.